this is John Black, Super Chemist. We're going to talk about gravity. We're going to talk about time dilation, okay? Because I think there's no such thing as a gravitational field, okay? That's a lie, okay? The whole thing about this video is about the time dilation thing, okay? So if there's no gravitational field, then well, how do you get time dilation? This is the first thing I want to bring up, okay? They show these videos, right? And they'll have here, this will be the planet, right? And they'll have a clock here, and then they'll have a clock here, and a clock here, and a bunch of clocks going all the way out to outer space. And they'll show how, look, as the clock moves away from, the planet, the time goes faster. And when you go closer to the planet, look, your clock goes slower. That's a lie. That only if there was a gravitational field would that be so. But it's not so. Okay, and the first thing I want you to bring up, but no one ever thought, hey man, how are those clocks floating there? How are they just floating all above the earth? And none of them ain't falling. No one ever said, hey, why ain't they falling down to the earth? I'll tell you why they ain't falling down to the earth. Because they're fictitious clocks. They're hypothetical. They're imaginary. They're fake. They don't exist. They're just there to prove a point that, you know what I mean? That, if you put clocks like that, okay, they will fall to the ground, okay? They will not just stay there and be in some gravitational field, okay? If you have to have two things happen to be time dilated, okay, near a planet, okay? There's only two ways, right? One is that if you could have the clock here, and a whole bunch of them going out to outer space, you know what I mean? If they're all attached to a pole, and that pole is attached to the Earth, right? Now, when you look at the clocks, you will see this clock is slower than this clock, and this higher you go, the faster the clock goes. Why? Because you're in the frame of the reference of the planet. While you're falling, you're in an inertial frame. You're not actually falling because you're following that geodesic that I was talking about, right? While you're following that geodesic, you are not actually moving through space. You're only moving through time. Get it? So you're not actually accelerating to the ground. You're keeping the same spatial coordinates you had. The spatial coordinates, the actual space-time that you're in, your little bubble there, yeah, that bubble's moving. You relative to the bubble, you're not moving at all. You know what I mean? You're not accelerating at all, not in any way, shape, or form. So how can you be time dilated? Time dilation is only from acceleration. There's no such thing as a gravitational field, okay? So how's the second way that you could be time dilated? You can be attached physically to the Earth and be in the same frame of reference, or you can be in a different frame of reference, but have the same exact acceleration as the Earth. You know what I mean? So my point is, those clocks, you got your Earth here, and you got a clock here. If you put a rocket on all those clocks, instead of attaching them to a post and then attach the post to the Earth, right? If you put a rocket on all of them, and their rocket is good enough to accelerate them away from the Earth, okay, because you're going to be going away from Earth, but they stay the same distance from Earth. Let's say they're 10,000 miles away from Earth, right? And obviously they're going to follow that geodesic, and they're going to stay in space. They're going to stay floating there, but in time they're going to start moving along that geodesic, which is bent towards the Earth, and it's going to fall, right? Well, if you have the clock is at 10,000 feet, right? He puts its rockets on. Now he has the rockets just enough to overcome that geodesic, okay? And stay there. But not enough where he's flying off away from the Earth, right? He has his rockets on the entire time, accelerating, but he stays in the same spot because all he's doing, he's only overcoming the gravity, the geodesic. That's all it's doing. So he will have, if you put it this way, if you have a 10,000 mile post and you put a clock on it, right? So it's attached to the Earth, right? And you have another clock over here in a spaceship, and he's not attached to anything, but has his rockets on, so he floats exactly right there where that other clock is. It's attached to the post to the Earth, right? Now these two clocks will both be time dilated at the same exact rate, because even though this spaceship is not in the same frame of reference as the Earth, it's accelerating at the same rate, that you'd have to be, you know what I mean? So the two frames are different frames, but they're the exact same type of frame because they're both accelerating at the same rate, right? And you could say, well, when you're attached to the Earth, you do that pull and you put the clocks on, up and up and up. You're not accelerating. I don't see any acceleration. You don't have to see acceleration for something to be accelerated. This is so stupid. When you are in flat space-time, you can just stand still there and not do anything. But if you're in curved space, right? The only way you can keep your same spatial coordinates relative to the rest of the universe, right? So when you're following that geodesic, right, you're moving relative, say, to the Earth, right? So when you're in curved space-time, to keep your same coordinates relative to the rest of the universe, you need to be accelerating, okay? This is a fact that people don't understand. If you are in curved space-time, you have to accelerate to keep your same spatial coordinates compared or relative to everything else in the universe, right? Meaning the planet, right? Like those clocks floating above they'll fall to the ground. They have to have a rocket, because they're in curved space-time. So in order for them to stay the same distance, right, same distance away from the planet, they need to be accelerating. If you're in curved space-time, you need to be accelerating to stand still, okay? You know what I'm saying? To overcome that geodesic, you need to, because that geodesic is accelerating you somewhere, down to the Earth, you know what I mean? It's accelerating you. So you have to accelerate the same amount just to stay in the same position, okay? So when the Earth is accelerating out, if it didn't accelerate out, it would get crushed. It would be smaller. So it has to. So the Earth is accelerating outwards at 9.8 meters per second, okay? Space-time itself, space-time itself is constantly accelerating downward into the planet, right? And it just disappears. Just like dark matter, it creates space-time in between the galaxies, right? Where did that space-time come from? No one knows. We don't know. I don't know. Where does that space-time go when it goes into the planet? I don't know where it goes. I don't know. I have no idea. All I know is it's shrinking because of the mass. And I know that the dark energy, the space-time there, it's growing because of lack of mass. You know what I mean? No one knows why. No one never will know why, probably. But because of that fact, right, if space-time is contracting or shrinking or accelerating in an accelerated way, right, inward, and the Earth is accelerating at the exact same rate outward in the opposite direction, then you won't see the movement. You'll never see the Earth expand and blow up because they're doing it at the same rate. Look at this. I'm pushing down on this hand, right, with a certain amount of force. I'm pushing up on this one. I'm still pushing. Do you see anything moving? No, I'm standing still. But I'm still forcing it. It's still happening. You know what I mean? It's the same way with the Earth. It accelerates outward. You don't see it because at the same exact time, it's only accelerating outward by electromagnetic forces because it's being crushed by the space-time. The space-time is literally being curved in on itself. And so, think about it. I'm planet Earth. Here's the two geodesics that I make. I make this from the North and the South Pole, right? I make two geodesics. Now, the South Pole and the North Pole are both going to go try to be at this focal point. Both of them, if they travel through time, Earth would be crushed, and they both, North and South Pole will be right here at this point, right? That don't happen though. That don't happen because you can only crush something so much, and once you crush it so much, that's how planets. How do you think planets get so compact? It's because they're constantly crushed by the space-time being curved down, okay? And then the Earth goes through time, and it can't fit in that, because you can see when you make them two geodesics, the area or volume, it gets smaller and smaller. The Earth can't fit in there. It just gets crushed. But you can crush it so much, electromagnetic forces are going to start, right? And push out, accelerate out. So that's why there's no such thing as time dilation from acceleration and gravity, because there's no such thing as a gravitational field, right? The truth is, there's only time dilation when you're talking about acceleration. That's it. There's no other type of freaking time dilation. And I don't want to hear about some other weird going off on a tangent. We're talking about gravity and acceleration. Them two things, there's no time dilation except from acceleration, because there's no such thing as gravitational field. The gravitational, if you're flying, you're just floating through space, right? Then you start coming by this planet, right? Your clocks all around you are going to be the same. Even though you're in this imaginary gravitational field, there is no gravitational field. So your clocks in your ship that's just floating will never be affected by it. Never. When you come up to the Earth, right, you get too close, and you're following this geodesic, right? But that geodesic that is pushing you towards, that's the time one. You don't see that. There's not actual any movement in the time thing, right? We just graph it on a thing, and it looks like he's moving, but it's not, you know what I mean? When he falls and he's accelerating towards the Earth, it's not happening for him. For him, he's in his little bubble, his little space-time bubble, and he's staying in the same space-time. It's just the space-time itself is accelerating downward. Why? Because the space-time in between that coordinates and Earth is shrinking. It's disappearing. It's going away. Just like dark matter, but dark energy does, just creates space-time. We don't know how. This is the same way. It just, when you have a big planet, it just gobbles up, When you see that thing, when they show you that graph, right, and there's an apple here or whatever, and here's the Earth, and then they show that geodesic, right? They show that geodesic. All that area, like this, here's my geodesic, right, down to the planet. All this area under here, underneath that geodesic, it's disappearing. It's shrinking. That's the whole deal. That's what people don't understand about this curved space-time model, right? They think that when you draw that geodesic, the apple just is following that geodesic down. No. You can take the apple out of the equation, right? And let's just call that spatial coordinates at the top of the geodesic, right? Where the apple was. Let's call spatial coordinates D, okay? Yeah. We can take the apple out, and guess what? Spatial coordinates D will still follow the geodesic. The geodesic is not the path of the object falling. It's the path of space-time itself falling or accelerating towards the Earth. Yes, it also is the path of the apple if there's an apple there. Okay? But my point is, that even if you take the apple out, the geodesic is still there, and something is traveling in it, and it's called space-time. And if you notice, it keeps getting closer and closer to Earth, this geodesic. Why? Because the stuff underneath, the space-time underneath, it shrinks. It gets smaller. It disappears in the planet somehow. I don't know how. Maybe it pops out in the other galaxies that are coming out, and that's what creates space. And that's where the space-time comes from. Because of dark energy. I don't know. I don't know. Nobody knows. No one's going to know. But I do know this. Mass gobbles up space-time. Just like, because of positive curvature in space-time. Okay, and dark energy. That's it.